Hi, Professor Lamb here is another video, PiPad Mathematics. This video is on the locker problem and the extension that you have for the locker problem related to factors. There's other videos, another video that I have on the locker problem itself that goes into some detail about how to do it. I'm just going to show just some other ways real quick how you can use some other iPad apps to help teach this. Well, alright, so starting off, this is the Color Tiles app from BrainingCamp, and what you can do is just taking a simpler problem. Let's just say we have locker numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we have 12 lockers here, not drawing lockers, and what we're going to do is I'm going to show you how you can help record the process. Now, real quick, the problem itself is you're in a school, the janitor there's 20 lockers, or in this case there's 12 lockers in a row, and the janitor has closed all of the locker doors, and we'll call them, Dr. Lamb's math class decided we're going to do a little experiment. We're going to send 12 students, and they're going to open or close locker doors given certain criteria, where the first student must, since all of the lockers are closed, the first student must go and open all of the lockers. The second student will go to the second locker and close it, go to the fourth locker and close it, and go to every second locker after that and close those doors. The third student would go in and start at the third, and since the third one was closed, I'm having a little brain problem. Since the third one was, alright, so the first one went and opened them all. Yes, so the third one's open, and so the third student will close the third one, and then the sixth one was open, was closed, so it's open it. Alright, the idea is that each student number is going to change the state of that particular locker. So the third's going to go every third one and change the state. The fourth is going to go to every fourth one and change the state. The fifth is going to go every fifth one and change the state. We can illustrate this on the app to where all the doors are closed. And so the first student is going to go in and open them. So I'm going to put green for open. So we're opening the first door, we're opening the second, we're opening the third, we're opening the fourth, we're opening the fifth, opening the sixth, opening the seventh, opening the eighth, opening the ninth, opening the 10th, the 11th, and then the 12th. Then the second student comes in, and so that was first student, student 1. The second student's going to come in and it's going to change the state of every second door. So we're going to go to the second door here, and it was open, so we're going to close it. We're closed. Then we're going to go to the fourth, and we're going to close the fourth. We're going to go to the sixth, and we're going to close the sixth. We're going to go to the eighth and close the eighth. We're going to go to the 10th and close the 10th. We're going to go to the 12th and close the 12th. Wait, I did this. Some of you noticed it already. Erase that one. That's good. And then this was the first student. This is the second student. Okay? Now we go to the third student. And the third student's going to go to the third locker. So this is 1, 2, third locker and change its state. Well, it was open, so we need to close it. So I'm going to take my third and we need to close the third one. Okay? And then we're going to go to the sixth one right here, and it's closed, so we need to open it. Alright, when we go to the ninth one, it's open, so we need to close it. We go to the 12th one, it is closed, so we need to open it. And then the fourth student's going to come in, fourth student, and it's going to go to the fourth door, and notice that it's closed, so we are going to open that one. And then the 5th door is open, so we're going to close that. Oh, sorry, I did that wrong. 4th student doesn't go to the 5th door. It goes to the 8th door, and it's closed, so we're going to open that one. And then we're going to go to the 12th door, and it's open, so we're going to close it. And then we go to the 5th student. He's going to go to the 5th door, and it's open, so we're going to close that one. And then we're going to go to the 10th door, and it's closed, so we're going to open that one. And then we got the 6th student. 6th student is going to come in, and we were at the 6th door, and it's open, so we need to close that one. And then we go to the 12th door, and it's closed, so we need to open that one. I didn't do that right. This goes up, undo, close that, go over here and grab it, and it goes up there. Alright, now we go 7th student. 7th student's going to come over here to the 7th door, and it's open, so we need to close that. And then we don't have any other doors, so the 7th student is done. And then we go to the 8th student. 8th student's going to the 8th door. It's open, so we need to close it. 9th student is going to go over to the 9th door. It's closed, so we need to open it. Let me zoom out just a little bit. 10th student is going to go to the 10th door, and it's open, so we need to close it. And then the 11th is going to go to the 11th door. It's open. We need to close it. That's 11th. And then the 12th student is going to go over to the 12th door. It's open, so we need to close it. And now you have a diagram with your color tiles of opening and closing. And the locker problem, it illustrates that all the perfect squares are still open after everybody goes through. So perfect squares are open. And then we look at the number of changes is, or I should say, are the factors. Okay? So the number of changes represent the factors, meaning the factors of 6 are going to be 1, the number 2, the number 3, and the number 6. So there are 4 factors. The problem number 6 has, or the number 6 has 4 factors. The number 9 has 1, 2, 3 factors. The number 11 only has 2 factors, 1, 2. So the idea is that you see that prime numbers only have 2 factors. Square numbers have odd numbers of factors, or in this case like 3, 9 has 3, and then all the composite numbers have even number of factors. And you can find out which ones change the most, and notice that the problem number 12, or number 12, has the most factors, and it has 6 factors. So locker problem goes in and does factors, okay? And the extension to all of that has to do with how do you determine how many factors, any number would have. So if we wanted the number 123, how many factors does 123 have? If we wanted the factors 117, how many factors do 117 have? 263. So these are questions that we need to ask, and the locker problem, we could do the problem all the way out. If we're trying to find out how many factors 473 has, then we can do the locker problem for 473 students, and then count how many times the 473rd locker changed its state. That would be a long way. It would be a long way to get to Dallas, if you will, to go that route. So is there a faster route, or is there a way to get there a little bit sooner? And there is. So what I'm going to do is, I'm going to open up, explain everything, and with explain everything, we'll come in, add a new one. We'll use a black background, and the extension to the locker problem, locker extension, the locker extension, okay, has to do with primes prime numbers and raising prime numbers to exponents. Okay, so we can identify our prime numbers, and we need to look for patterns. So when you're teaching this, you do certain things like you give students an opportunity to help develop that pattern and learn that rule, if you will, and then find out how they can apply that rule. So you have something, we'll take prime numbers. We have a prime number of 2 raised to the first power, and then 2 raised to the second power, and 2 raised to the third power, and 2 raised to the fourth power. And what we want to do is, we want to see how many, so the exponent, okay, so when a base of 2, a prime number, is raised to a certain exponent, how many factors does it have? Okay? So let's work it out. 2 raised to the first power, so an exponent 1, how many factors does it have? Well, 2 raised to the first power, it equals 2. Equals 2. So the factors of 2 are 2 and 1. 2 and 1. So the number of factors, we'll call number F, is going to be 2. Alright? What about 2 raised to the second power? Well, 2 raised to the second power is 4. We raise it to the second power, exponent of 2. And the number of factors, well, the factors of 4, which is 2 squared, are going to be 1 times 4, so 1 and 4, and then 2 times 2, so just 2. This has 3 factors. Okay? 2 raised to the third power, so an exponent of 3. 2 raised to the third power is 8. Factors of 8 are going to be 1 times 8, 2 times 4. So it has 4 factors. And then 4, exponent of 4, 2 to the fourth power is 16. What are the factors of 16? 1 and 16, 2 and 8. How about 4 times 4? So it has 5 factors. Okay. What do we see here? What kind of patterns do we recognize? One of the patterns that we want to understand is that given the exponent of that prime base, a prime base, how does that connect or get you the number of factors? Okay, so of that prime base of 2 in this case, we had an exponent of 1 and we got 2 factors. When we have an exponent of 2, we got 3 factors. When we have an exponent of 3, we have 4 factors. An exponent of 4, we get 5 factors. So a rule would be we have the exponent exp plus 1 gives us the number of factors. So we have a pattern here with a base of 2. Does it work for other prime numbers? Well, we can certainly check it out. Other prime numbers, let's just do, how about, I don't know, 8. 8's not prime. That's a terrible number. Come on, Professor Lamb. Let's go up to 3. So 3 raised to the first power, 3 squared, 3 raised to the third power, 3 raised to the fourth power, and let's see if our rule holds true. Well, 3 raised to the first power is going to be 3. That has 2 factors. So my rule, 1 plus 1, does give me 2. Okay, so it works for 3 raised to the first power. Let's try it out with 3 squared. 3 squared is 9. The number of factors of 9, well, we got 1 and 9, and we got 3 times 3. So we have 3 factors. And does our rule work? 2 plus 1 does give us 3. So far, so good, working with our rule. Let's see, if we go here, 3 raised to the third power is 27. So factors of 27 are 1 times 27, 3 times 9, and that's it. So I got 4 factors. And then does our rule hold up? You take the exponent, you add 1, and that tells you how many factors there are. And let's assume here you add 1 to that, we're going to get ourselves 5 factors. Okay, so our rule is holding up. And our rule works mathematically when there is a base, a prime base, prime number base. And then you take the rule is you're going to take the exponent plus 1 equals factors. Okay? So if you have a prime number and you know the exponent of that prime number, you can tell how many factors that prime number has. And you think, well, why is that? Where does that come from? Why can't you just take the exponent plus 1? Well, you think about a prime number is just itself and 1. The factors are itself and 1. Well, so I got a prime number, and then the factors, if we did like a factor tree, prime number here, we would get the prime number, and then we would get the number 1 over here. Okay? And if I were to raise that prime number to an exponent, in other words, multiply it by itself again, or add or multiply whatever exponent it was times that prime number again, we would in essence get another prime number in here. We'd come down here and we got a prime number. And then we come down again and we have another prime number. We multiply it times another prime number again, and each time those prime numbers have, it's just prime and 1. So like 7 raised to the first power, and you multiply that times 2, that gives you 7 raised to the second power. You multiply that times 7, not 2, and that's going to be 7 to the third power. Okay? And so you have 7 to the first power times 7 gives you 7 squared. 7 squared times 7 gives you 7 to the third. And the idea is that every time you multiply it times this 7 here, you're going to get a new factor. Okay? It's going to be whatever 7 squared times 7 is. So 7 to the third. So 21, or I'm sorry, 49 times 7. So every time you multiply it by that base again, the product is the only new factor that you get. So every time you multiply times that prime number again, you only are adding one new factor, okay? And which is going to be the product of your original, like 7 to the, or 7 squared times that 7. So the exponent tells you how many factors there are, or the number of 7s there are, or the number of that prime number multiplied times itself. That tells you how many of those you have. You got 7, and you got 7 squared, and you got 7 to the third, so you got 3 of them there. Let me say that again. So 7 to the third. Your factors, if we listed them out, would be 7. They would be 7 squared, and they would be 7 to the third. Those are your 3 factors. These 3 are your exponent. The plus 1 for the number of factors is that 1 sitting right over there. Is the original is just that 1 that is a factor of all your whole numbers. So I hope I said all that right. The idea or the concept here is you have any prime number, and when you raise it to an exponent, that exponent itself tells you all of the factors when taking the base times itself. The plus 1 is the factor of 1. Okay? So how does that extend to the locker problem? Well, any number that you have, any whole number that you have, you can have a prime factorization. And once we have it in prime factorization, we can then determine how many factors it has because of this rule we just discussed. So if you have a number 360, okay, the number 360, let's just say we had a locker problem, 360 lockers, 360 students. How many times does the 360th locker changes its state? How many times does it open and close? Well, it would take us a long time to do the locker problem. But if we know that if we can break this number down into prime numbers and prime numbers raised to exponents, then we'd be able to find out how many factors 360 has. And that's what we're doing here. We take 360, that's going to be 36 times 10. 36 is going to be 9 and 4. 9 is going to be 3, 3. 4 is 2 and 2. And this becomes 2 times 5. So we have our prime factorization, and we can write that as 2 raised to the third power times 3 squared times 5. Okay. Now we have prime bases raised to exponents, and we can determine how many factors each one of them has. So plus 1, that means I have 4 factors there. Plus 1, that means I have 3 factors there. And this is going to be 1 plus 1, understood 1 exponent. It's going to give me 2 factors. So if I have 4 factors sitting here with my base of 2, 3 factors with my base of 3, and 2 factors with my base of 5, then, like problems similar to the outfits and things like that, and how many different ways you can make an ice cream sundae, we have 4 possible factors here combined with 3 possible factors there combined with 2 possible factors there. That is a multiplication problem. We got 4 groups of 3, 4 times 3, and then that answer is going to give you 12 groups of 2. So we end up just multiplying the number of factors by each of them. And that's going to give us 12 times 2, because 4 times 3 is 12. And now we have 12 groups of 2 going with the 2 factors of 5, and that is our 24. So 360 has 24 factors. So any number, any whole number, when you break it down into prime factorization, you can determine how many factors that number has. And so that would be the locker problem extension. There you have it. Thank you for watching. Again, Professor Lamb, PiPad Mathematics.